Folks, welcome to chapter 4, second lecture. Yesterday, in the first lecture of chapter 4, we did talk about the ionization processes. What is ionization? I hope you well understand. Formation of ion is ionization. Normally, a molecule is neutral, but when an electron is ejected out of the molecule or it is absorbed by the molecule, it makes positive or negative ion. The sources of ionization we also talked yesterday. In fact, the whole of our universe is full of ion, that is full of electricity. Electrons and ion are the tiny little particles which carry the electricity. On our earth, we are full of ionization. As I mentioned right in the beginning of our lectures, you clap and you produce ion. You rub your shoulders or your clothes with your own hand, you produce electricity, charge, and that is ion and electrons. In the atmosphere, because of the friction, because of the cosmic ray irradiation, photon presence and photon irradiation, we have all around us electricity, and ionization keeps taking place. We are full of charged particles all around. But what concerns us here is the process of ionization under electric field. How does, when you apply the voltage to an electrode resting in a dielectric, how does the process of formation of ions and other charged particles begin? So first step which lead to breakdown is certainly ionization. There is no doubt about it. But ionization is not simple. Ionization won't produce a breakdown. Initial process of ionization in gaseous dielectrics caused by electric field is known as electron avalanche. When the ionization process begins let's talk first about gaseous dielectrics. There is under the influence of the electric field, there is an exponential growth of the charged particles. And these charged particles develop in the form of an avalanche, which we learn today. Depending on the magnitude of the applied voltage, the electron avalanche will develop. For achieving complete breakdown in any dielectric, it is the advanced stage when an unlimited growth of conduction current is caused. I mean, in the breakdown, unlimited growth of current, that is, what is current? It's nothing but the flow of charged particles. So we need vigorous ionization process to achieve the required magnitude of the current to achieve breakdown. Sustained and non-sustained discharges are there. We'll learn about it. Then these are described by some scientists with their own understanding. The basic discharge process leading to breakdown in weakly non-uniform fields and uniform fields is very similar. We will first understand the process in just a minute. The process of discharge process we learn in uniform field and in weakly non-uniform field, which is very similar, unlike the discharge process in uh, in uh, extremely non-uniform field. We learn about all. Just a minute, if I can make a small stopover. I need something which I am not getting. Puneet, yeah. Uh, okay, we can proceed. Uh, the development with the development. Oh, yeah, I got it. Yeah, development of electron avalanche. How does it uh, begins to form? Initially, the electrons are obtained in a gaseous dielectric uh, uh, space, dielectric gap space between two electrodes, either by ionization of neutral molecules, by photons from cosmic rays, or ultraviolet illumination of the cathode, or at a later stage by photons from the discharge itself when the electric field is applied. Yeah, I'll explain what it is meant there. When you take two parallel plates and you apply some voltage, the process of avalanche formation, that means the process of ionization, will not begin unless there is an initiatory electron available. The main source of uh, ionization under electric field is the kinetic energy by acquired by an electron. So presence of an electron in the gap is must. If it is not there, it may require very high voltage to be applied to begin the ionization process. But at the reasonable voltage to begin the ionization process, presence of an initiatory electron is very necessary. And that you can achieve if you irradiate, for example, the electrode surface with the help of an ultraviolet illumination or by source of photons from cosmic rays, you will be able to get an initiatory electron in the dielectric when you irradiate the surface. And once under the influence of the electric field, the process of ionization starts, it will carry over of its own. I mean, it will develop of its own the further process. And when you keep on increasing the voltage, the vigorous ionization process would take place. The electrons thus generated accelerate towards the anode. Electrons generated in the dielectric on the surface of the cathode, they get accelerated, they move towards the positive polarity, you can say the electrode anode, gaining kinetic energy on the way and because of the movement from applied electric field between the electrodes. The kinetic energy thus acquired by the electrons can be high, that on colliding with a neutral molecule in the gas, it may ionize them. When it ionizes, it is known as elastic collision. It may happen if the kinetic energy is not enough, the magnitude of kinetic energy in the electron is not enough, it may render a neutral molecule to a higher excited or vibrational state. It may not ionize, but render the molecule at excited state, we call it, and that is an inelastic collision when the ionization is not successful. When an electron gains more energy under the influence of the electric field, more energy than required for ionization of the gas molecule, because the gas molecule, different gas molecules, uh, different gases, the ionization energy required by the electron is different. Every gas has got its own characteristic. Then it is capable of ionizing when it is more than the required minimum energy. That is, ejecting an electron from the neutral molecule and leaving behind a positive ion. The new electron thus ejected out of the neutral molecule, along with the primary, repeat the process of ionization, both of them. And that is why it is known as an exponential growth of ionization. So long an electron would keep on making successful or elastic collision, so long its energy is greater than the minimum energy required for the particular gas for ionization. That is in electron volt. The table was given in the earlier lecture. The new electron thus ejected along with the primary keep on making the ionization process. And since a molecule is much heavier as compared to the electrons, the velocity of electrons is something like 150 times more than that of the molecules, because of the mass of the electron, difference in the mass of the electron and molecule. So electrons are much faster, that's why they have much higher kinetic energy and they move very fast. Their speed is something like 10 to the power of 7 centimeters per second, unlike something around 10 to the power of 5 centimeters per second for molecules. When there is such a large difference in their speeds, in a small gap, you can consider the molecules to be more or less stationary, whereas the electrons are continuously moving towards the anode. So the electron, it can be considered relatively stationary. The molecules can be considered relatively to be stationary, making no contribution to the ionization process. It is only the electrons making the or taking up the ionization process. On the contrary, electrons move very fast under the influence of applied electric field and continue to release further electrons from the gas molecule. This is a typical picture how what I explained minutes back. Development of electron avalanche, a swarm of charged particles develop. As you can see, at the cathode, you initiate the process with an initiatory electron, and it hits the molecule, ejects another electron. Both of them hit further molecules and eject electron. That is how a swarm of charged particle is produced in the gap between the cathode and the anode, and the electrons move towards the having negative charge of electricity, they move towards the positive electrode. Development of electron avalanche as given by Townsend. Townsend conducted his experiment more than 100 years back. In something like 1914, he conducted his experimental investigations, and later then also derived equation, mathematical equation for the development of current or the growth of current in the gap. The Townsend's experiment, one should never forget that these were conducted in, of course, there was a concept of uniform field even at that time between two parallel plate electrodes forming a uniform field. And second thing, he conducted his experiments in very small gap distance, which has its own conclusions. We'll come to that. So the Townsend's theory, if only the process of electron multiplication by electron collision, that is elastic collision, is considered in uniform field between two plates, then neglecting other processes, that is recombination and diffusion of charged particles, the number of electrons produced by collision on at an element dx between the plates at a distance x, you can write dnx is equal to nx alpha dx. Here, nx is the number of electrons at distance x from the cathode, and alpha is the average number of ionizing collision produced by an electron in moving unit distance. Alpha is the Townsend's first ionization coefficient. It was given by Townsend and known as the Townsend's first ionization coefficient. And if n naught, the number of electrons set out of from the electrode, this is n naught, the number of electrons set out of electrode, then we can derive the equation further in this with this. Yeah, then nx is equal to n naught e to the power of alpha x, as we had explained that it is an exponential growth of electrons. So the number of electrons at a distance of x in the gap from the cathode, beginning with total number of electrons n naught, would be given as n naught e to the power of alpha x. And this is true in uniform field where the field intensity E is constant minded. This is a very important thing one should never forget. The ionization coefficient alpha can be considered also constant because of the uniform field. Otherwise, it is not constant in extremely non-uniform fields, field conditions. By integrating this equation 1 and applying the initial condition nx is equal to n naught, and at n naught at x is equal to 0, the following equation is derived, as you can see, nx is equal to n naught e alpha x. This was not performed in weakly non-uniform fields by Townsend, but later people studied this phenomenon in weakly non-uniform fields also, because the concept of weakly non-uniform field developed much later. So in the weakly non-uniform field, the same expression can be rewritten as you can see here, nx is equal to n naught exponential of alpha is changing in weakly non-uniform field from in the distance from 0 to x dx, and this would give rise to n d is equal to n naught e alpha d. That is when x is equal to d, that is the gap distance between the two electrodes. D is the gap distance between the two electrodes. It has been also found and established that alpha by P is equal to F E by P. P is the pressure of the gas, you can say. E is the pressure of the gas. Yeah, here you see this develops in the form of an avalanche. This is, as you see, the sketch here is an electron avalanche, and the constant field intensity E naught between the cathode and the anode is given, and this is a very typical shape of the electron avalanche. As you can see, the positive ions in this case, let's consider this to be happening in air. So the positive ions, which are more or less stationary or which stay back at the back of the avalanche, are at the tail of the avalanche, and head of the avalanche is formed by the electrons, and a kind of a wedge-shaped electron avalanche because of the scattering of the electrons in every direction. This acquires a typical shape. Is it not something interesting that this single avalanche has been photographed with great difficulties and techniques by Rather, as you can see in the next figure, an electron avalanche in uniform field. The first one, of course, distribution of charge, carriers, and the shape, and the second one, actual photograph by the scientist Rather somewhere in the middle of the 20th century. The Rather, a German scientist, he could record. It is very difficult to record or to photograph a single avalanche, or even to give rise a single avalanche. You can imagine if you increase the parameters like applied voltage and more number of initiatory electrons presence, the number of electrons would be given rise. But to have photographed a single avalanche is something creditable. Now, just a minute. Yeah. Just a minute. Yeah. Now the breakdown mechanisms. The breakdown with avalanche discharge, simple avalanche discharge, was given by Townsend, and it is known as Townsend's mechanism. Breakdown with streamer discharge or streamer or canal mechanism was given later, for applicable for longer gap distances, because the phenomenon we will learn took a different shape when the gap distance was increased. The whole phenomenon of the development of the breakdown mechanism, initial breakdown, development of breakdown mechanism, completely changed. The breakdown mechanism given by Townsend confines to very small gap distance, and we call it a avalanche discharge. It was caused to be, and we will learn also one more thing, that this in very small gap distance, it took place with avalanche formation of below critical amplification. As you can see, when you increase the gap distance, when you apply more voltage, the size of the avalanche would increase. So there a critical size of the avalanche has been also mathematically described. And in all Townsend's work, it was the electron avalanche amplification was small, was below that is termed as below critical amplification. So when the distance d between the two electrodes in uniform field is very small, alpha, the Townsend's first ionization coefficient, which is a function of field intensity E, may still have quite a low value, even at the breakdown field intensity. What will it render to? For achieving breakdown, you require very large number of charged particles. That is vigorous ionization process. That means vigorous formation of the charged particle, that is electrons and ions. But in very small gap distance between the two electrodes in uniform field, it was found that the alpha process alone, which is taking place in the gas, is insufficient to generate the required number of charged particles required for the current or the breakdown current, which is very, very high. So Townsend gave a thought over it, and Townsend has observed that current increased more rapidly with increase in voltage as compared to the one given by the equation what we had derived. Then another thought came in his mind, that production of sufficient number of charged carriers in the gap under such conditions is possible only by secondary ionization process. So he gave his explanation what is the secondary ionization process. The secondary ionization process begins with three processes of cathode effect, which are described quantitatively by he gave another coefficient and known as the gamma coefficient or the secondary ionization coefficient. And this gamma comprises of three processes or the three cathode effects, you can say. That is, it is defined as the mean number of secondary electrons released per positive ion incident on the cathode. The positive ions at the tail of the avalanche fall back on the cathode and give rise to another phenomenon, when that is gamma ion, and when the photons are produced in the process, gamma photon, that is photon effect, is considered to be, and gamma m is the metastable. M stands for metastable. The metastable particles, because of the inelastic collision made by some electrons, metastables, when they fall back to their original thermal energy, they also give rise to charged particles. And the total gamma is the sum total of gamma ion, gamma photon plus gamma metastables. It strongly depends upon the cathode material. That is because this is a cathode effect. So the material of the cathode would strongly affect in this case, and it is a function of field intensity and pressure of the gas also, just like the primary coefficient alpha. Gamma is also a function of E by P. That is Townsend's secondary ionization coefficient gamma, which is defined as the mean number of electrons released per positive ion incident on the cathode when they fall back on the cathode. So this is where something very interesting, the cathode effect and the cathode material effect is taken into consideration. Only with alpha and gamma taking place together, the required number of charged particles in the gap could be produced for the breakdown current. Yeah, this is, as you can see, these are the equations. We will come to this equation, and just a minute. Yeah, we'll come to this equation. Yeah, as you can see, the growth of current, the schematic on the left side, the current versus voltage. When you increase the voltage, the growth of current is in three parts. As you can see, the initial I naught, the magnitude of I naught current depends upon the initial irradiation of the electrode. Then when you increase the voltage further here, you see the part 2, that is the alpha coefficient, that growth of current because of the Townsend's first ionization coefficient. So the equation of the current in this part is I is equal to I naught e to the power of alpha x or alpha d. Then this equation would have given rise to a magnitude of current this much only, which does not convey an unlimited growth of current in the gap. For that, the third part of the curve, that is this part of the curve, is given in more charged particle by gamma process. In the second part, alpha process takes place, and the further rise in the current when you increase the voltage, the gamma process, that is the cathode effect, comes into picture, and you get an unlimited rise in the current magnitude in the gap, and you accomplish the breakdown. So this was given the schematic by Townsend, which has been later measured by many scientists. For example, this is on the curve on the right shows on helium at pressure of 488 torr, the growth of current in uniform field by increasing the voltage. And this was done here in 1963, something like more than something like 50 years later, what Townsend had given. At the time of Townsend, there might have been a constraint to be able to measure the current, such low magnitude of current as developed initially in this process. Yeah, Townsend's current growth equation in this third region is derived as follows. N naught, the number of primary electrons, photoelectrons emitted from the cathode at x is equal to 0 per second. In other words, an avalanche in uniform field develops at the cathode with n naught initial electrons, as we talked about. Let n naught prime be the number of secondary electrons produced at the cathode per second. N naught is the primary electrons, we say, and N naught prime is the secondary electrons produced per second at the cathode, that is the gamma effect. And N naught double prime is the total number of electrons leaving the cathode per second. Then we can write the equation N naught double prime is equal to N naught plus N naught prime. And when we write the equation further, that since each electron leaving the cathode makes on an average e to the power of alpha d minus 1 collisions, because 1 is the number of that electron itself in the gap distance of d. Therefore, the total number of ionizing collisions per second in the gap will be equal to n double prime e alpha d minus 1. By definition, gamma is the number of secondary electrons produced on an average at the cathode per ionizing collision in the gap. Therefore, n naught prime will be equal to gamma n naught double prime e alpha d minus 1. In this way, when we substitute, we can get n naught double prime, that is the total number of the charged particles reaching the anode, will be equal to n naught plus gamma n naught double prime and n naught whatever. Yeah, n naught double prime e alpha d minus 1. Now you can get on the other side, n naught double prime will work out to be n naught upon 1 minus gamma into e to the power alpha d minus 1, which gives you the total number of electrons reaching the anode initiated with n naught electrons, considering both the gamma as well as alpha processes. So the number of electrons arriving at the anode is given by we can take nd is equal to n naught double prime e alpha d. So nd will be equal to n naught e to the power alpha d upon 1 minus gamma e alpha d. So the equation works out to be by putting the value of n naught double prime in the equation equal to nd, the equation works out like this. Under the steady state conditions of this experiment, the current in the gap can therefore be, total current in the gap can be given as I is the total current, you can say, is equal to I naught e to the power alpha d upon 1 minus gamma e to the power of alpha d minus 1. So this is a general equation of current growth considering both the alpha as well as gamma processes. And this equation describes the growth of average current in the gap before the breakdown. According to this equation, gamma E alpha D minus 1 in the denominator of the equation represents can be represented by mu, another constant mu, which is defined as the mean number of secondary electrons produced per avalanche. Mu is the mean number of secondary electrons produced per avalanche. mu will always be less than 1. As you can see, the value of mu will always be less than 1. The secondary ionization or gamma process is significant. Then equation reduces to I is equal to, sorry, I read it wrongly. When the gamma process is insignificant, mind it. If the gamma process is insignificant, that is the cathode effect, material effect is not there, then the equation reduces to I is equal to I naught E alpha D, which represents the region 2, as I explained in the curve. Yeah, in this curve, the region 2, as you can see here, that is the alpha process. Then we go back. Yeah, the applied voltage and hence the field intensity is low in this region of 2. This condition is also described as non-self-sustaining discharge, as given the expression by Townsend, as I was mentioning earlier. Non-self-sustaining discharge. That means it is not attaining its ultimate goal, or ionization process, under which a breakdown would not be able to develop by itself. That means alpha process is insufficient to be able to develop to the breakdown. As the applied voltage and thus the field intensity E is increased, the value of mu approaches to 1. Then the denominator of the equation approaches to 0, and therefore the current I tends to rise unlimited rise will be there. In this equation, as you can see, when mu E alpha D minus 1 approaches to 1, then there is when this this equation gamma E alpha D is equal to 1, so denominator is 0 and there is an unlimited rise in the magnitude of the current. Yeah. At this stage, when the denominator of this equation tends to be 0, the current is, however, limited by something, and that is nothing but the impedance offered by the power supply and the gas itself. That is the circuit impedance, you can say. They will be sublimited. The current won't grow infinitely, but it will be limited by the impedance in the circuit. Under these conditions, the discharge or ionization process becomes self-sustained, as Townsend puts it, to maintain the level of required charge carriers described by self-sustained discharge. And the quantitative condition for breakdown can be expressed, therefore, when mu, for the breakdown to be able to take place, mu is equal to gamma into e to the power of alpha d minus 1. It tends to be equal to 0, which means what? That this equation is known as Townsend's criterion for spark breakdown in uniform field. At the final stage of the breakdown, the electron amplification is normally much greater than 1. So E alpha D is much greater than 1. So 1 we can neglect here 1. So the Townsend's criterion for breakdown reduces to gamma E alpha D is equal to 1. So we can stop here for today, and tomorrow we will discuss the streamer criterion for breakdown. Thank you very much.